Hi, my name is Kang Zuheng.
My name is He Yayun.
We are from Ping An Technology. Today we are excited to present our paper
Feature-rich audio model inversion
for data-free knowledge distillation
towards
general sound classification. This is a data-free knowledge distillation framework optimized for general sound classification.
Before we introduce data-free knowledge distillation, we need to know about knowledge distillation first. Imagine you have two robots, one big and one small. The big robots has learned how to do a lot of things, and the small robot wants to learn too. The big robot shares what it knows with the small robot, and the small robot uses that knowledge to learn. This is called knowledge distillation. In simple terms, knowledge distillation is when a small model, called the student, learns from a big model, called the teacher. The student copies the teacher's behavior to get a simpler understanding of the knowledge the teacher has.
Now, what if the small robot doesn't have any data to learn from? That's where the data-free knowledge distillation comes in. The big robot still acts as a teacher, but instead of using the data to show the small robot what it knows, the big robot generates the predictions for a set of inputs. The small robot then tries to replicate those predictions as closely as possible, so it can effectively learn to perform the same as the big robot. This technique helps the student learn from the teacher without needing the original data. This is useful when data is not available or when sharing is not allowed. Data-free knowledge distillation creates fake data to teach the student to act like the teacher. This is especially important when you want to use machine learning on devices with limited resources, like smartphones or smartwatches. The smaller model can run faster and use less power, but still give you the good results. Also, in private areas, such as health, where privacy is important, data-free knowledge distillation helps teach without sharing private details. That's the power of data-free knowledge distillation.
Data-free knowledge distillation has done something amazing things in computer vision. But it hasn't made any breakthroughs in audio and signal processing. Image and audio are intrinsically different. Firstly, images have a fixed dimensionality, but audio model doesn't. Second, we are trying to generate large spectral in a traditional model inversion. The feature distribution in the time dimension is usually very sparse. It means that only a few features in a short period of time are enough to determine its category. So we need to find a model inversion method that can guarantee the feature richness of the generated audio samples in the time dimension. And we also need to design a mechanism that can effectively use these feature-rich samples in knowledge distillation to improve recognition accuracy.
Before explaining our proposed framework, we need to understand the method of contrastive inversion. In order to produce the training data, the synthetic audio is generated by the model inversion shown in the yellow spectral. To prevent the model from generating too many identical samples and to ensure the diversity of generated samples, we can use the contrastive inversion, which tries to make the currently synthesized samples as different as possible from the historically synthesized samples. In practice, we can set a memory bank to store the historically synthesized samples. Then, the currently synthesized samples should be as different as possible from the samples stored in the memory bank. Especially, we can set the current sample as the anchor point and all the samples in the memory bank as a negative sample. Then, the anchor point samples and the negative samples can be mapped into a common embedding space by a pre-trained teacher model. In this space, the feature embeddings of the anchor samples are as far as possible from the negative samples.
The framework described above works well enough for images, but causes some problems for audio. In particular, for time-independent audio signals like environmental sounds. The signals are usually stable and their contents are usually consistent. However, in practice, the synthesized samples usually contain only few features, which is sufficient for classification but not enough for training. Therefore, we need to guarantee the feature richness of each generated part of the synthesized data. To deal with this situation, we propose a feature invariance contrastive inversion method to solve the above problem. Specifically, the current synthesized data is first cut into K tracks in the time dimension shown in the red, green, blue spectrum. Then each track is converted into embedding by a pre-trained teacher model. According to the characteristics of time-independent audio, the audio features in each block should be similar. In other words, their feature embeddings should be as close to each other as possible. Based on this, we construct a feature invariant contrastive inversion loss to get the model to synthesize feature-rich and reliable audio samples, and ultimately achieve higher classification accuracy. This is the reason why we propose this method.
To make use of these feature-rich samples, we can actually do much more. In a general sound classification task, there's usually a statistics pooling layer to eliminate the time dimension. Before the statistics pooling layer is the frame level, and after is the utterance level. However, in our last approach, we only used the utterance level information, but lost the frame level information. If the information before and after the statistics pooling layer can be used simultaneously, it can help student model learn better from the teacher model. Here, we firstly obtain information on both frame level hidden states and utterance level hidden states. Then, the mean and the variance of these two types of hidden states are calculated separately. Eventually, the student model can gain a more comprehensive knowledge from the teacher ever than before.
Here we show our experimental results as 3 audio datasets, respectively. From the table above, it can be seen that the teacher outperforms the student at knowledge distillation when trained with data. However, in the case of data-free, deep inversion performs very poor, much worse than other methods. The framework we proposed is basically stronger than knowledge distillation, and even better than the accuracy of the teacher shown in the red numbers. In our analysis, the model inversion not only restores real samples, but also mixes various features to create more samples with richer features.
Let's hear some generated samples. From this demo, we can see that the samples generated by deep inversion is noisy and the generated features are sparse. While using the contrastive inversion, the generated samples are much smoother, but the audio features are still sparse. After using our proposed method, the audio features become very rich.
Next, we listen to the generated spoken digits from 0 to 9.
0, 1, 2, 3, 4, 5, 6, 7, 8, 9.
We can hear that the synthesized samples are clearly discernible to the human ear.
We hope you enjoy our paper. If you have any questions, please let me know. Thank you.
If you like our paper, please cite us. Thank you.